Next up is Mike Gisclair with FEDCO, and he is going to present his presentation entitled Using Turbochargers for Interstage Boosting and BWRO Applications. So Mike, the floor is yours.
Thanks for the introduction, and thank you for participating. So a quick introduction to FEDCO. FEDCO is a pump and energy recovery device manufacturer. We've been in business since 1997 with thousands of references on 6 continents. We offer custom engineering as standard on our pump and turbocharger lines with global parts and service support from our headquarters in Monroe, Michigan. So how do Interstage turbochargers improve system performance? Well, let's start with some of the advantages and how it is implemented. Using a turbocharger as an Interstage booster can improve system performance and recovery. It can extend membrane life. Now let's go to a little more detail to how that happens. By applying energy where it is needed, you can manage things such as fouling layer and boundary layer in RO that are a result of high lead element flux. By increasing recovery, we can reduce brine disposal. Implementation is simple and affordable for new build and retrofit systems, with design and installation support, and a 36-month warranty is standard on all turbochargers. An example of this is the Seacoast Utility Authority in Florida. A new water source challenged system performance due to higher feed TDS. This is common in plants operating on wells. As wells draw down over time due to high drawdown or due to drought conditions in that area, the well water becomes increasingly saline, which changes how the system performs. So a retrofit Interstage turbocharger was applied for pressure boost, essentially getting the second half of that RO, the second stage of that RO, to contribute to system operation. And as a result, recovery was optimized for a wide range of feed conditions. So I mentioned earlier about how Interstage boost can improve the operation of RO. Let's go a little more detail about that. So to your right, you see a diagram of a standard 2-to-1 2-stage membrane array typically used in brackish water RO applications. Without Interstage boost, feed pressure drops as osmotic pressure rises with increasing feed salinity, resulting in a net decrease of net driving pressure. Now, many system designers will apply excess or extra feed pressure to the lead of the RO in order to account for this, such that the tail elements are producing. But these high element fluxes contribute to fouling layer and boundary layer with an effect on salt passage, osmotic pressure, and long-term fouling and scaling. By balancing velocity and flux, by applying energy where it is needed with an Interstage booster, we can restore the net driving pressure to the second stage, such that the net driving pressure or the applied pressure is placed where it is needed, when it is needed. In much the same way as a 2-stage RO today manages velocity by vessel count. For example, if you have a 2-to-1 vessel count, as you get to the second stage, you reduce the number of vessels to improve the velocity. Well, in the same way, applying Interstage boost applies pressure where it is needed. Imbalanced RO is inherently inefficient, but balanced RO is efficient not only from an energy perspective, but also from a mass perspective. So what is a turbocharger? A turbocharger is a kinetic single-stage energy recovery device. It converts brine energy to feed boost without brine mixing, with a straightforward low-maintenance design. One moving part, a rotor, with a brine control valve for flexible transfer of energy. In short, a turbocharger converts pressure to velocity, velocity to power, power to velocity, and velocity to pressure. So let's go a little more detail into that. A turbocharger is a radial inflow turbine direct coupled to a single-stage centrifugal pump. The nozzle of the turbocharger converts brine pressure to velocity. A volute maintains velocity around the rotor. The rotor converts that velocity to power, which is then transferred to the feed pump impeller by way of a shaft. Again, pressure to velocity, velocity to power, power to velocity, and velocity to pressure. So how is a turbocharger applied in a multi-stage RO system? The diagram to your right shows a turbocharger location within a two-stage RO, essentially acting as an interstage booster, a brine-driven interstage booster that restores the net driving pressure to the second stage, turning what used to be an energy loss in the form of a brine control valve into a pressure boost that restores balance to the RO system. In this way, turbochargers do not require electrical power input or auxiliary equipment, and they can readily accept high inlet pressures. So in design of a turbocharger, there are two key kinetic factors in variable operation. And again, brackish water RO plants often encounter very variable conditions that you typically don't see in seawater RO. For example, as the wells become drawn down, salinity increases. You may see variations with drought, for example, that you typically don't see in seawater RO. So how does the turbocharger account for this? In turbochargers with an integrated auxiliary control valve, the CV, or the coefficient of velocity through that nozzle, can be varied by opening or closing the auxiliary control valve, essentially accounting for variations in brine flow and brine differential pressure across the nozzle. So how does it benefit the operator? How does it benefit the end user? How does it benefit the ratepayer? So this slide shows a two-stage 24x16 7M array with and without interstage boost for a fixed feed salinity of 3,000 ppm at 80% recovery and a system flux of 12.8 GFD. Interstage boost reduces the feed pressure from 311 psi to 284 psi, while increasing the second stage feed pressure from 297 psi to 330 psi. Now this balances the flux. The first stage flux without boost is 14.2 GFD. The average flux on the second stage is 10.6. But by applying interstage boost, the fluxes are balanced now at 13 and 12.5 GFD respectively. For a pump efficiency of 83%, the pump power is reduced from 162 kilowatts to 143 kilowatts. At 10 cents per kilowatt hour, that amounts to a savings of $16,644 and a return on investment of 2.26 years. In short, balancing an RO, applying energy where it is needed, is cost-effective and efficient. So in summary, interstage turbochargers improve system performance and recovery. They can extend membrane life and reduce brine disposal. If you think about it from a mass balance perspective, all brine is a loss from an efficiency perspective. If you're discharging your water in the form of brine, that's a water loss. That's a net loss to the system. Implementation is simple and affordable for new build and retrofit, with design and installation support, and again, a 36-month warranty is standard on all turbochargers. And with that, I thank you for your time and welcome any questions.
Thank you very much. I appreciate it, Mike. I do have a question for you.
Sure.
Coming off of that presentation, curious what if I need more interstage boost than available from the brine energy to the turbocharger?
Good question. Thank you.
What then?
So if you think about a turbocharger essentially as being a single station trivial pump with a rotor prime mover, applying a motor to the turbocharger such that now that pump impeller has two prime movers, you can apply additional energy to that rotor, to that pump impeller, such that you can achieve higher pressures or more consistent pressures than what is available from the brine energy. Alternatively, you can also recover energy from that turbo. So for example, say you need 30 PSI or 40 PSI of interstage boost to balance out the system, but you've got 300 PSI of brine pressure available. That's probably more than enough to achieve interstage boost. By putting a motor on the turbocharger and using a regenerative VFD, that energy, that brine energy, can then be recovered and put back to the bus or to the grid for a net energy reduction on the plant as a whole.
Well, I will say net energy reduction is always a topic of interest for almost everybody in the industry. So we appreciate you clarifying that, and thank you very much. A lot of good information in that presentation, Mike. Thanks very much.